Torvalds has always been like, no, no, no. We know how to do this. We're doing it the old traditional way that we know works. It's going to be C code. And recently, Rust has managed to become an approved language where there's code in the kernel right now, and new device drivers for new USB devices, let's say, can be written to be Rust device drivers, again, in the hope that they won't crash as much.
Huh, that's interesting. I didn't know that. Cool. Awesome. Thank you. Thank you. All right. All right. So hopefully the screen looks better. I upgraded to Nitro so that I could get the 1080 and 1440 with a higher frame rate. So hopefully it's good for everybody. We will jump right into it. I'm going to go ahead and share the Google Colab for those who don't have it right now, so you could actually fork your own and code along. And yeah, we're right at the end of the chapter. So we're basically, what did we end up with yesterday? So yesterday we chose a model. We chose the linear regression model. It wasn't powerful enough. We ended up moving to a different model, a decision tree regressor. And so it turns out that the linear regression model was underfitting and this one was overfitting. That's where we left off. So I think the last thing we did was we applied the mean root squared error cost function to try to make it more accurate, or yeah, try to make it more accurate. But yeah, we left off where it was overfitting. So we'll start off right here. Anyone have any questions before we get started? Cool, cool. Let's get right to it then. So better evaluation using cross-validation. One way to evaluate the decision tree model would be to use the train test split function to split the training set into a smaller training set and a validation set. Then train your models against the smaller training set and evaluate them against the validation set. It's a big effort, but nothing too difficult, and it would work fairly well. A great alternative is to use Scikit-Learn's k-fold cross-validation feature. The following code randomly splits the training set into 10 non-overlapping subsets called folds. Then it trains and evaluates the decision tree model 10 times, picking a different fold for evaluation every time and using the other 9 folds for training. The result is an array containing 10 evaluation scores. I'll go ahead and type that. Feel free to code along or throw some comments out there if you would like.
Okay, if I read ahead a bit?
Yeah, do your thing.
Scikit-Learn's cross-validation features expect a utility function, greater is better, rather than a cost function, where lower is better. So the scoring function is actually the opposite of the root mean square error. It's negative values, so you need to switch the sign of the output to get the RMSE scores.
Cool. Feel free to keep going if you want. I'm just going to print this out here.
So we can look at the results. Now the decision tree doesn't look as good as it did earlier. In fact, it seems to perform almost as poorly as the linear regression model. Notice that cross-validation allows you to not only get an estimate of the performance of your model, but also a measure of how precise this estimate is. That is, its standard deviation. The decision tree has an RMSE of about 66,868 with a standard deviation of more than 2,000. You would not have this information if you just use one validation set, but cross-validation comes at the cost of training the model several times, so it's not always feasible. If you compute the same metric for the linear regression model, you will find that the mean RMSE is a little higher, more than 59,000, and the standard deviation is about double. So the decision tree model seems to perform very slightly better than the linear model, but the difference is minimal due to severe overfitting. we know there's an overfitting problem because the training error is low, actually 0, while the validation error is high.
Let's try one last model now, the random forest regressor. As you'll see in Chapter 7, random forests work by training many decision trees on random subsets of the features, then averaging out their predictions. Such models composed of many other models are called ensembles. They are capable of boosting the performance of the underlying model, in this case decision trees. The code is much the same as earlier. Feel free to type out or continue reading if you'd like.
Jim, can you like scroll up this screen?
Is that good or more?
Like the book screen. Can you scroll it up?
Yeah. More?
No, currently the book chapter which you're sharing is not complete, right? After ensembles, like they are capable of boosting per. I mean, after that, what's the text?
I think the screen's lag.
Yeah, the screen might be. Hey, can you see it?
Oh yeah, now I can see it.
Okay, cool. Yeah, it was lagging, which it shouldn't be because I have I pay for good service here, so it shouldn't be doing that.
I'd say more frozen than lagging.
Yeah, which it shouldn't be happening. Did you want me to scroll up more, or is this good?
Yeah, it's good. Do you want me to read? Like, I think. Do you want me to read from that? Wow, this is much better.
Yeah, that's fine. I'm almost done here.
Okay, so this is like I mean the results. So this is much better. The random forest really looked very promising for this task. However, if you train the random forest and measure the RMSE on the training set, you will find roughly 17,474. That's much lower, meaning there is still quite a lot of overfitting going on. Possible solutions are to simplify the model, constrain it, that is regularize it, or get a lot more training data. Before you dive much deeper into random forest, however, you should try out many other models from various categories of machine learning algorithms. Example, support vector machines with different kernels and possibly a neural network without spending too much time tweaking the hyperparameters. The goal is to shortlist a few, that is 2 to 5 promising models.
So before we leave random forest, I'll just put in a commercial plug for XGBoost. If you give me any random forest model and XGBoost is in the mix, I would bet on XGBoost winning for accuracy.
What is SGBoost?
XGBoost is just yet another Scikit-Learn compatible library. You can do a pip install.
Gotcha.
It deliberately follows the same calling procedures for training and fitting and then doing inference.
Copy that.
There's a rich literature on random forests, and if I could summarize the literature, I'd say that XGBoost seems to be more robust than most approaches to random forest.
Okay.
So it's basically that random forest, but with the boosting technique, right? There's a technique called as boosting, right?
Give me 1 second.
Yeah. But there's a lot of details, paying attention to variance, memory consumption, and speed of training, speed of inference. The literature goes into a lot of details on all of it.
Yeah. I know there are like two concepts in machine learning, bagging and boosting, which are which basically kind of helps you regularize your model, or like helps you reduce the errors in your model. so which are used in machine learning a lot.
Oh yeah, clearly they're distinct concepts, but as a practitioner, I would sort of view bagging and boosting as almost the same. It's sort of answering the question, how can I make more of my data?
Correct, yeah. Yeah, that's why I think when you said XGBoost, is it like it is used to do that? Or like it's just like, okay.
For a while, AdaBoost, AdaBoost was one of the leading algorithms, and XGBoost came along and ate its lunch.
Give me 1 second. Make pipeline, pre-processing, random forest. All right. Cool, cool. All right, so let's assume that you now have a short list of promising models. You now need to fine-tune them. Let's look at a few ways you could do that. Grid search. One option would be to fiddle with the hyperparameters manually. Until you find a great combination of hyperparameter values, this would be a very tedious work, and you may not have the time to explore many combinations. Instead, you could use Scikit-Learn's Grid Search CV class to search for you. All you need to do is tell it which hyperparameters you wanted to experiment with and what values to try out, and it will use cross-validation to evaluate all of the possible combinations of hyperparameter values. For example, the following code searches for the best combination of hyperparameter values for the random forest regressor. Feel free to continue reading if you'd like. I'm just going to go ahead and type this out here.
Notice that you can refer to any hyperparameter of any estimator in a pipeline, even if this estimator is nested deep inside several pipelines and column transformers. For example, when Scikit-Learn sees pre-processing GeoN clusters, it splits this string at that double underscore. Then it looks for an estimator named pre-processing in the pipeline and finds the pre-processing column transformer. Next, it looks for a transformer named Geo inside this column transformer and finds the cluster similarity transformer we use on the lat-long attributes. Then it finds this transformer's n clusters hyperparameter. Similarly, random forest max features refers to the max features hyperparameter of the estimator named random forest, which is of course the random forest model. The max features hyperparameter will be explained later in chapter 7. Wrapping pre-processing steps in Scikit-Learn pipeline allows you to tune the pre-processing hyperparameters along with the model hyperparameters. This is a good thing since they often interact. For example, perhaps increasing n clusters requires increasing max features as well. If fitting the pipeline transformers is computationally expensive, you can set the pipeline's memory hyperparameter to the path of a caching directory. When you first fit the pipeline, Scikit-Learn will save the fitted transformers to this directory. If you then fit the pipeline again with the same hyperparameters, Scikit-Learn will just load the cached transformers. I'll do that.
I wonder why this is taking so long. There might be an error in my code.
It is taking long. It's because for every fold it is doing like multiple forest regressions, so it is going to be slow.
It will take a lot of time.
Yeah, it will take a lot of time. It's doing like a lot of computation.
Okay.
I'd make another commercial plug. One of my favorite libraries for slow things is called Toxim, TQDM. You pip install Toxim. And the reason it's so cool is that if you have, like, for I in something big, you can say for I in TQDM something big, and it'll throw up the progress bar showing, you know, how many hours it's going to be until it finishes.
You think I should start throwing sponsors into the videos? Just playing.
It's free software.
I'm just
Just
playing.
saying I like it.
I'm just playing.
Comes in handy all over the place. Well, just forge ahead. There are two dictionaries
Do your thing.
in this param grid. So grid search CV will first evaluate all 3x3 equals 9 combinations of n clusters and max features hyperparameter values specified in the first dict. Then it will try all 2 times 3 equals 6 combinations of hyperparameter values in the second dict. So in total, the grid search will explore 9 plus 6, or 15 combinations of hyperparameter values. And it will train the pipeline 3 times per combination, since we're using threefold cross-validation. This means there will be a grand total of 15 times 3 equals 45 rounds of training. It may take a while, but when it is done, you can get the best combination of parameters. On the other hand, if you have 45 hosts on some cloud provider, then it goes quicker.
Can I ask a question before we go any further? You said that there's a massive amount of computation happening here. Why is this? I feel like I have a good CPU and it should be quicker. Is it because it's happening on Google Colab servers and they're like capped or something like that if it's free?
You're using Google Colab server CPU.
Okay.
Change it to like GPU runtime. Then it will be fast.
Here?
But if you change to GPU, you will have to run.
Yeah, now
and
don't do it.
Yeah, I think it's done already. The 10 iterations.
So what's actually happening here? Why is it taking so much computation?
Okay, so random forest is itself very complex. A decision tree is complex, and plus you are applying random forest, which is a combination of decision trees, and plus in that you are taking cross-val score, and the default value is 10. So it is happening for 10 subsets of training set and 10 subsets of corresponding validation sets. So overall, this is a big iterative process, I believe, which is why it is taking.
Yeah, but Deep, like if we use like GPU runtime, it would be a bit faster, right?
GPU will definitely be a bit faster, and in some cases GPU will be, I believe, 3 or 4 times faster too, like in specific cases of neural networks or something like that. But I am actually yet to try GPU for machine learning or something like that, like for training random
so
forest.
in Google Colab, like I usually do that, like in Google Colab.
Yeah, they provide a free Tesla T4, right?
So I could actually program it to use my GPU instead of using Google's GPUs, which would be better.
Is it like you're still running? Yeah, next time you can just change it to GPU.
And I could run it on my hardware.
Oh, okay. So here's a bit of a catch. I myself bought a new laptop a few days ago because of Black Friday thing, and to set your NVIDIA GPU locally for, I mean, so that you could work in Anaconda or something like that, you'll have to scale down versions, and you'll have to, because it doesn't support Python 3.11 onwards, so you'll have to scale down your Python, your TensorFlow version to 3.10, and you'll have to follow a rigorous documentation of TensorFlow or probably Scikit-Learn.
Okay. I'll do that another time, so it's not during the book club, and it'll probably make the book club quicker for next time.
So it makes sense that humans get impatient when there's a delay. And a good rule of thumb is if you're going to run it once or 45 times, time running it once and make a prediction that if I do this 10 or 45 times, it'll take maybe 10 or 45 times longer. And so, just like we chase down bugs, did I get the expected results displayed? We also chase down performance bugs. Is it running slower than I anticipated?
Mm-hmm. Grid search CV. estimator. Okay. All right. So where were we? Down here, right? You just read. Was it this one you just read?
Yeah, I could pick it up. In this example, the best model is obtained by setting n clusters to 15 and setting max features to 8. Because he's patient and he let it run all the way through. Since 15 is the maximum value that was evaluated for n clusters, you should probably try searching again with higher values. The score may continue to improve. This is kind of a special case of it's easy to interpolate, it's quite a challenge to extrapolate. It's hard to predict what's going to happen off the end of your graph. You can access the best estimator using gridsearch.bestestimator. It happens that it has an underscore. They have a naming convention in that way. So you can access the best estimator with best estimator. If grid search CV is initialized with reset equals true, which is the default, then once it finds the best estimator using cross-validation, it retrains it on the whole training set. This is usually a good idea, since feeding it more data will likely improve its performance, typically by reducing variance. The evaluation scores are available using grid search CV results. This is a dictionary, but if you wrap it in a data frame, you get a nice list of all the test scores for each combination of hyperparameters and for each cross-validation split, as well as the mean test score across all splits.
The mean test RMSE score for the best model is 44,042, which is better than the score you got earlier using the default hyperparameter values, which was 47,019. Congratulations, you have successfully fine-tuned your best model. Go ahead if you want. I'm just going to type this out here.
Yeah, so randomized search. The grid search approach is fine when you are exploring relatively few combinations, like in the previous example, but randomized search CV is often preferable, especially when the hyperparameter search space is large. This class can be used in much the same way as the grid search CV class, but instead of trying out all possible combinations, it evaluates a fixed number of combinations, selecting a random value for each hyperparameter at every iteration. This may sound surprising, but this approach has several benefits. First, if some of your hyperparameters are continuous for discrete or discrete but with many possible values, then you let randomized search run for say 1000 iterations, and then it will explore 1000 different values for each of the hyperparameters, whereas the grid search would only explore a few values for each values you listed for each one. Suppose a hyperparameter does not actually make difference, but you don't know it yet. If it has 10 possible values, you add it to your grid search, then the training will take 10 times longer. But if you add it to a random search, it will not make any difference. If there are 6 hyperparameters to explore, each with 10 possible values, then the grid search offers no other choice than training the model a million times, whereas random search can always run for any number of iterations you choose. Okay. What does it mean? Whereas the random search can always run for any number of iterations. Okay, so it's randomly defining an iteration rather than giving some fixed iteration. Is that right?
I understood the part that randomized search. I understood the difference that grid search is more rigorous and thorough, goes through each and every combination, and randomized search series it will pick randomly. But the last point says that grid search will go through a million times, and in random search you can run for any number, and they've also mentioned n iterations. Oh, okay. I got it what they're trying to say. Okay, so random
That's
search tool.
the number of iterations is something like which you can define randomly,
Yeah,
right?
yeah,
To
yeah,
use.
yeah, yeah, yeah.
Yeah,
And it will
yeah,
choose those combinations randomly. So
yeah.
I mean,
But
we can
that,
put two. Mm-hmm.
but the thing with that is, uh, like you have to like. I mean, what if like you don't choose the best possible hyperparameter solution? Because then, if like, how can you be sure that the one which you have picked randomly is the best?
I think this will again be, the way you define your parameter grid. The more diverse it is,
Correct.
then
Yeah.
you apply randomized search CV, and you give probably n iter or number of iterations is 10, then it will randomly pick 10. But if you, in the first place, if you put your dictionary, the parameter distributions dictionary only a bit uh, constricted, not containing diverse parameters, then I believe it has no option, right?
So how can you be sure it pick the best? You cannot. It will not pick the best.
Yeah, yeah. That's what I'm saying. So the I think its ideology is not to pick the best, but I would say to pick the one which gives you like diverse, like. So what would be like? I mean, yeah, that I understood that it's not to pick the best actually, because in order to pick the best, you need to go through every possible permutation, right?
Mm-hmm.
Yeah, I'm still thinking like
I
why they.
However, if you have limited computation budget, if you can only devote 5 minutes to this,
True, yeah, yeah.
then random search is likely to be exactly the right first stage to picking, quote, the best. And so you might give 3 minute budget to random search, and that will get you to the appropriate neighborhood. And then you might do an exhaustive grid search on a promising neighborhood, on a local optimum.
Correct. Mm.
So if I could throw out a literature keyword, Latin squares are a common technique for designing an experiment. Doctors run into this all the time. You want to like figure out, do I dose the patient with this many milligrams or that many milligrams? Do I dose them daily in the morning, or do I dose them every 2 hours? Do I dose them when they're on one dietary regime or one exercise regime or another? So there's all these variables that they could write down before they begin the experiment, before they design a protocol for clinical trials. And if you have a budget of 1,000 patients that you can try this on, even a handful of variables, like I just described 4 of them, could easily overwhelm your budget. You might have very little statistical power. You would only have maybe 2 or 3 patients that are in any one of those cells when you cut it so finely because there's so many variables. And a Latin square is similar to this random approach, where you deliberately create a mix of exploring all the variables, because some of them might not be informative. It might turn out that your exercise regime has 0 effect on the effect of the therapy. And so it could be very expensive to learn that it's uninformative, or you could sort of mix it in with all the other random variables.
Yeah, I mean, the thing which I'm reading is, it's more so like if you have a data set, not just like huge data set, but if it is like if it is like kind of continuous, which would be easy for you to statistically distribute the data, then random search CV would be much better, because your data is kind of like continuous. So that would perform better, because one thing is it's huge, so grid search would be like more exhaustive. But if it's continuous, then like, yeah, what you said, like, in that case randomized search would perform better. Not always, but yeah, sometimes.
Well, even if you have categorical values like high, medium, low, or Boolean, it's still worth your while to do randomized search across them, because you might think that an input variable is informative, and it turns out it's not. It turns out it doesn't affect your target value at all. And you can learn that cheaply by mixing it in with the other experiments that you're running as part of this batch that will reveal the top couple of informative variables.
Okay. Yeah. I still have to read about it. I'm going to read about it and then see. Yeah. But yeah, that was clear.
Yeah, share what you learn when you come across those answers too. I'm curious.
Yeah, I am going to like go through this notebook once again, like later on, to understand like at least the hyperparameter tuning part, because that was like I know what grid search is. I've used that, but I just want to understand what random search is in more detail. But yeah, I got a whole like a high level overview of what exactly it is.
Yeah, same. I definitely want to circle back and just dig a little deeper into some vocabulary as well. Cool. We're on. Oh, go ahead.
Another keyword is distractor variable. Data scientists hate distractors because they're meaningless. They have no effect on the target value, but they gum up the works. They hang out in your data set, and if you were doing a grid search, you might waste a lot of time trying every possible value for some distractor variable, and you would learn nothing because it's uninformative.
I mean, you can remove the distractor variables by just simply doing some EDA and finding out all the significant variables, which is basically affecting the model, or like using some correlation. That would help you to like remove the distractor variables. Like you don't have to like before even grid search doing, you can actually remove those distractor variables, right? The one which is not affecting the
not always.
Not all of them, yeah. I mean, everything cannot be removed because those distractor variables might be not correlating with the output variable, but might be correlating with some other input variables. So you have to keep them because that would affect the model in some way.
Copy that.
But the distractor means you're talking about the insignificant variables, right? Which are not affecting the model actually. Like,
that's correct.
Yeah. Okay.
And you know, if you want to be mean to your model, if you want to be mean to a random forest, you can always inject your own distractors. It's easy to make up random columns and tack them on the side of your data frame and see if your model does the correct thing, see if your model ignores it.
Specifically to try to distract your model to see its reliability?
Yeah.
Huh. Okay.
So for example, in a random forest, you might have 100 columns, and if you look at the winning trees, you might notice that there's 6 or 8 variables that seem to always appear in the winning trees. The ones that cross-validation reported had good scores. And from that, you would conclude that the other 90 plus columns were distractors.
Huh.
And you can sort of ground truth that. If you made up random columns on your own, so you know for a fact that those columns are having 0 effect on Y, the desired value, then you can verify that the random forest, correctly ignored them.
Yeah, that makes sense.
If it does not ignore them, it suggests that maybe N is too small, that it's overfitting on sort of tiny amounts of samples in each of your tiny cross-validation folds.
Okay. So we are here, right? Ensemble methods. Another way to fine-tune your system is to try to combine the models that perform best. The group or ensemble will often perform better than the best individual model. Just like random forests perform better than the individual decision trees they rely on, especially if the individual models make very different types of errors. For example, you could train and fine-tune a k-nearest neighbors model, then create an ensemble model that just predicts the mean of the random forest prediction and the model's prediction. We will cover this topic in more detail in Chapter 7. analyzing the best models and their errors. You will often gain good insights on the problem by inspecting the best models. For example, the random forest regressor can indicate the relative importance of each attribute for making accurate predictions. Feel free to keep reading unless you're typing code too. I'm almost done with this one here.
Yeah, let's sort these important scores in descending order and display them next to their corresponding attribute names. So, with this information, you may want to try dropping some of the less useful. Okay.
Go ahead.
The Scikit-Learn feature selection select from model transformer can automatically drop the least useful features for you when you fit it. It trains a model, typically a random forest, looks at its feature importance attribute, and selects the most useful features. Then, when you call transform, it drops the other features. Okay. You should also look at the specific errors that your system makes, then try to understand why it makes them and what could fix the problem, adding extra features or getting rid of uninformative ones, cleaning up outliers, etc.
Now is also a good time to ensure that your model not only works well on the average, but also on categories of districts, whether they're rural or urban, rich or poor, northern or southern, minority or not, etc. Creating subsets of your validation set for each category takes a bit of work, but it's important. If your model performs poorly on a whole category of districts, then it should probably not be deployed until the issue is solved. Or at least it should not be used to make predictions for that category, as it may do more harm than good. I'm just going to copy this here.
So the item on try to understand is kind of a big deal. We call this diagnosis. You want to diagnose what's wrong with your model, why it doesn't match the real world. And it's much better to spend a few minutes thought to figure out what is my model not seeing? What have I not given to my model? Or what alternate model should I be using here? Better to do that than to start tweaking hyperparameters all day until you get your errors below some arbitrary figure.
So when it says that evaluate the test set, it means the validation set, right? Not like the one which we broke the main data into like test, training and test. So that test set, right? Not like the one which basically has no classes. It needs to have classes as well, right? The test set.
I thought they were talking about the test set, and when you do that, it's an expensive operation because you're kind of using up some of your test data. Hopefully, you've got maybe a source of daily sales data or something else that you can keep getting additional test sets.
Yeah, but they are already labeled data, right? The test set as well. It's labeled, right? Like with having the output value as well, right? Output variable value.
Right. Right.
Yeah.
Feel free to keep reading if you'd like.
Test and validate is your model has never seen tests before, and so it's a surprise what the score is going to be.
True.
So I'll just pick up.
Yep.
Evaluate your system on the test set. After tweaking your models for a while, you eventually have a system that performs sufficiently well. You're ready to evaluate the final model on the test set. There's nothing special about this process. Just get the predictors and the labels from your test set and run your final model to transform the data, make predictions, then evaluate these predictions. In some cases, such a point estimate of the generalization error will not be quite enough to convince you to launch. What if it is just 0.1% better than the model currently in production? You might want to have an idea of how precise this estimate is. For this, you can compute a 95th percent confidence interval for the generalization error using SciPyStat's T interval. You get a fairly large interval from 39,000 to 43,000, and your previous point estimate of 41,000 is roughly in the middle of it. If you did a lot of hyperparameter tuning, the performance will usually be slightly worse than what you measured during cross-validation. That's because your system ends up fine-tuned to perform well on the validation data and will likely not perform as well on unknown data sets. That's not the case in this example, since the test RMSE is lower than the validation RMSE. But when it happens, you must resist the temptation to tweak the hyperparameters to make the numbers look good on the test set. The improvements would be unlikely to generalize new data. Now comes the project pre-launch phase. You need to present your solution, highlighting what you've learned, what worked, and what did not, what assumptions were made, and what your system's limitations are. Document everything, and create nice presentations with clear visualizations and easy-to-remember statements. For example, the median income is the #1 predictor of housing prices. In this California housing example, the final performance of the system is not much better than the experts' price estimates, which were often off by 30%. But it may still be a good idea to launch it, especially if this frees up some time for the experts so they can work on more interesting and productive tasks. Pause a moment. Or I could keep going.
Yeah, you can keep going.
Launch, monitor, and maintain your system. Perfect. You got approval to launch. You now need to get your solution ready for production. That is, polish the code, write documentation and tests, and so on. Then you can deploy your model to your production environment. The most basic way to do this is just to save the best model you trained. Transfer the file to your production environment and load it. To save the model, you can use the joblib library like this, or joblib, dump. It's often a good idea to save every model you experiment with so that you can come back easily to any model you want. You may also save the cross-validation scores and perhaps the actual predictions on the validation set. This will allow you to easily compare scores across model types and compare the types of errors they make. Versioning both the data and the models usually is important and needs help from libraries that are good at assigning unique identifiers to them. Once your model is transferred to production, you can load it and use it. For this, you must import any custom classes and functions the model relies on, which means transferring the code to production. Then load the model using joblib and use it to make predictions. For example, perhaps the model will be used within a website. The user will type in some data about a new district and click the Estimate Price button. This will send a query containing the data to the web server, which will forward it to your web application. Finally, your code will simply call the model's predict method. You want to load the model upon server startup rather than every time the model is used. Alternatively, you can perhaps put in a dedicated web service that makes your web application can query through a REST API. See figure. This makes it easier to upgrade your model to conversions without interrupting the main application. It also simplifies scaling, since you can start as many web services as needed and load balance requests coming from your web application across these web services. Moreover, it allows your web application to use any programming language, not just Python. Another popular strategy is to deploy your model to the cloud. For example, on Google's Vertex AI, formerly Google Cloud AI Platform and Google Cloud MI Engine. Just save your model using joblib and upload it to Google Cloud Storage, GCS. Then head over to Vertex AI and create a new model version to the GCS file. That's it. This gives you a simple web service that takes care of load balancing and scaling for you. It takes JSON requests containing the input data, for example, of a district, and returns JSON responses containing the predictions. You can then use this web service in your website or whatever production environment you're using. As you will see in Chapter 19, deploying TensorFlow models on Vertex AI is not much different from deploying Scikit-Learn models. Let's keep going.
I could keep going if you want, or you could go. Up to you.
Yeah, I
You
can
can-
go. You're okay. So you're at the however, right? However, you may also need.
At but deployment.
Okay,
Right.
yeah, there's a lot of text. Uh, but deployment is not the end of the story. You also need to write monitoring code to check your system's live performance at regular intervals and trigger alerts when it drops. It may drop very quickly. For example, if a component breaks in your infrastructure, but be aware that it could also decay very slowly, which can easily go unnoticed for a long time. This is quite common because of the model rot. If a model was trained with the last year's data, it may not be adapted to today's data. So you need to monitor your model live performance. But how do you do that? Well, it depends. In some cases, the model performance can be inferred from downstream metrics. For example, if your model is a part of a recommender system and it suggests products that the user may be interested in, then it's easy to monitor the number of recommended products sold each day. If this number drops compared to non-recommended products, then the prime suspect is the model. This may be because the data pipeline is broken, or perhaps the model needs to be retrained on fresh data, as we will discuss shortly. However, you may also need human analysis to assess the model's performance. For example, suppose you trained an image classification model. We'll look at these in chapter 3 to detect various products defects on a production line. How can you get an alert if a model's performance drops before thousands of defective products get shipped to your clients? One solution is to send a human raters a sample of all the pictures that the model classified, especially pictures that the model wasn't so sure about. Depending on the task, the raters may need to be experts or they could be non-specialists, such as workers on a crowdsourcing platform, example Amazon Mechanical Turk. In some applications, they could even be users themselves, responding, for example, via surveys or repurposed captchas. Either way, you need to put in place a monitoring system with or without human raters to evaluate the live model, as well as all the relevant processes to define what to do in case of failures and how to prepare for them. Unfortunately, this can be a lot of work. In fact, it is often much more work than building and training a model. If the data keeps evolving, you will need to update your datasets and retrain your model regularly. You should probably automate the whole process as much as possible. How Here are a few things you can automate. Collect collect fresh data regularly and label it. Example, using human raters. Write a script to train the model and fine-tune hyperparameters automatically. This script could run automatically for example every day or every week depending on your needs. Write another script that will evaluate both the new model and the previous model on the updated test set and deploy the model to production if the performance has not decreased. If it did, make sure you investigate why. The script should probably test the performance of your model on various subsets of the test set, such as poor or rich districts, rural or urban districts, etc. You should also make sure that you evaluate the model's input data quality. Sometimes the performance will degrade slightly because of poor quality signal. Example, a malfunctioning sensor sending random values or another team's output becoming stale. But it may take a while before your system's performance degrades enough to trigger an alert. If you monitor your model's inputs, you may catch this earlier. For example, you could trigger an alert if more and more inputs are missing missing a feature, or the mean and standard deviation drifts too far from the training set, or a categorical feature starts containing new categories. Finally, make sure you keep backups of every model you create and have the process and tools in place to roll back to a previous model quickly in case the new model starts failing badly for some reason. Having backups also makes it possible to easily compare new models with previous ones. Similarly, you should keep backups of every version of your datasets so that you can roll back to a previous dataset. if the new one ever gets corrupted. Example, if the fresh data that gets added to it, if the fresh data gets added to it turns out to be full of outliers, having backups of your datasets also allows you to evaluate any model against any previous dataset. As you can see, the machine learning involves quite a lot of infrastructure. Chapter 19 discusses some aspects of this, but it's a very broad topic called ML operations, ML ops, which deserves its own book. So don't be surprised if your first ML project takes a lot of effort and time to build and deploy it to production. Fortunately, once all the infrastructure is in place, going from idea to production will be much faster. Yeah, I've heard about
I have two.
MLOps in another field actually. A lot of there are like job openings only for MLOps.
Really? That's interesting.
Yeah, just MLOps. We need MLOps. That's it.
Yeah, it sounds like a lot of work. It's reminds me of like it's just software ops, how important
It's
that
like
is,
DevOps,
setting up the infrastructure. That's interesting.
I have two comments on making backups beyond having some package support doing it in a regular fashion. When you persist a data set, always do it in a predictable order. Very often we'll do select star from table, and you want to have an order by at the end, and then that gets turned into a CSV often. So always use a predictable order so that you can conveniently diff this month's data against next month's data, so that like the new rows and the deletions, they show up in a predictable fashion. And then second item is also to support diffing. Often a pandas data frame will have annoying index numbers, 0 to however many rows, and when you persist, it's very often convenient to write out the rows comma index equals false to suppress that column so that it does not interfere with diff.
I mean, also like when it comes to keep on like automating the process of training your model with new data, I don't think it can be like a lot of times it cannot. I don't think it can be done on fly, because, for example, let's take ChatGPT. So the GPT model, the way they train it for ChatGPT, like I don't think like they have to like train it like not they cannot train it on fly. Like they have to like they need some time, because they need a lot of time to like train the model. So they need to keep like the old version running, and I think they use some kind of like I think they call it
So
the blue green deployment.
yeah. I mean, the first model took around 9 months or so. I mean,
Yeah.
all these bugs to run, and then the iterative process comes in where GPT is learning from the data which we put in, the users put in. So
Correct. Yeah.
this is how the entire thing becomes recurrent, and this is how actually the pipeline is to automate.
Yeah. The
Well,
process.
there are many models that can be trained incrementally or even trained on the fly, including GPT. It's just a matter of how they choose to do that very expensive process that consumes many hours of GPU time. So they've got more than 1 billion parameters. It's an unusually large model. For smaller models, it can be fairly easy to train as you go. There's also a technique called fine-tuning, where, say you have a neural network, you might choose to freeze the weights on the first several layers of the architecture, and then fine-tuning is using good enough responses coming out of the early stages, and the fine-tuning will only be responsible for adjusting weights in the last couple of layers.
Yep.
Yeah.
Yep.
Right.
We can leverage other models like using transfer learning and fine tune it again.
Yeah, basically the base models, you basically choose the base models, but you freeze some of the layers and just focus on like the softmax layers, the output layer, and just the layer before it, right?
cater our needs.
Yeah, correct.
Cool. Hopefully this chapter gave you a good idea of what a machine learning project looks like, as well as showing you some of the tools you can use to train a great system. As you can see, much of the work is in the data preparation step, building monitoring tools, setting up human evaluation pipelines, and automating regular model training. The machine learning algorithms are important, of course, but it is probably preferable to be comfortable with the overall process and know 3 or 4 algorithms well, rather than to spend all of your time exploring advanced algorithms. That makes sense. So if you have not already done so, now is a good time to pick up a laptop, select the data set that you're interested in, and try to go through the whole process from A to Z. A good place to start is on a competition website such as Kaggle. You will have a data set to play with, a clear goal, and people to share the experience with. Have fun. And then we have a couple exercises here. So yeah, how do you all want to proceed with this? I mean, we could go ahead and do something on Kaggle. We could go ahead and use a different source, or if y'all have any ideas that you have done before, or what are you thinking?
Because we'll get the data sets. So going for Kaggle would be like much faster to come up with the project rather than coming up on our own. But yeah, you guys can.
Okay. I mean, we do have a book club tomorrow. It's 7:18 right now, so we have about 10 minutes. I don't know if you want to jump into a conversation about what the project is going to be, but we could continue this conversation in the machine learning channel. Just start throwing ideas around. I could send a tag out to everyone who's been to the book club so far, saying we're starting a project, who has ideas on what they want to do as far as what the project is going to be. And then tomorrow we could dedicate that to actually discussing what the project's going to be and start getting that set up.
I would say like it would be like, since anyways we are thinking of doing it like off channel, we could like think of like forming like groups, because I mean like let's say like 10 people join that tomorrow's book club. So I mean, I don't think it would be a good idea for like all 10 people to work on one single project. I mean, like it's fine, but like I would say like working in groups or like that would be more helpful.
Mm-hmm.
Or like, yeah, I mean like we could do individually on that one project. That could be one thing to be done.
How many people per group you think? 4? 3 to 5 or something?
You don't need like 3 to 5, but I think 2 to 3 is fine. It depends on how complex the data set, or like how complex the project is, how complex the data.
3 will be the sweet number here.
Yeah.
Let me check out this Kaggle that they're talking about.
And we can only go for like regression project because we have learned regression.
Mm-hmm.
We can just check for regression models.
Okay. Just looking through the Kaggle website right now. It looks like it's a pretty solid community. They got competitions. Yeah, okay, cool. And then courses on top of that. Build your ML skills in a supportive and helpful community. All right. Data sets. Models. You said a linear regression model, right? Tasks. Image. So can we just type in linear regression?
Kaggle certainly has its charm. I'll just an interesting data set, a large data set that I've come across is a few years of COVID health data. Might be interesting to look at. There's an opportunity to sort of synthesize it along geography and time.
Okay, so exploring COVID health data. You're breaking up just a little bit. Is it just me, or is...
Just throwing it into the mix. There's certainly plenty of other things that one might look at.
Yeah. Okay, cool. Yeah, let me go ahead and I'll send a message out to everybody in the machine learning community and just see who's actually interested in doing this so we can see how many people we have. We'll break out into teams and then, yeah, so every team, I'm sure every team's not going to do the same problem. So every team will have a different problem that they solve. And yeah, if any one team gets stuck, there'll be hopefully at least a few other teams that could, answer questions or help them get through it. And yeah, we'll go from there. That sounds fun. That's gonna be exciting. It'll be cool to get our own project out there instead of just following the book. This is gonna be nice. Cool. All right. Well then, I'll see you all tomorrow at 6 p.m. Eastern Standard Time. Let me go ahead and send a message out right now, letting everybody know we finished the first chapter and we're gonna start our actual first project and see who wants to get involved, and we'll go from there. Yeah, we'll see where we're at tomorrow at 6, and yeah, if it's just us four again, then I guess this is the team. But if more people come, then we'll split out into groups. Cool.
Yep.
Alrighty. Have a good one, guys.